Okay, let's start. Yeah, welcome to everybody. My name is Fengler. I'm the chairperson of the joint working group for PIDIM. And within ABB, I'm in the division for measurement and analytics, and they are head for cybersecurity. I will show now a short introduction for PIDIM, as well what is on our roadmap. PIDIM for process analyzers and instruments. Mainly we are discussing about devices, so to identify common parameters covering primary field devices. And the target is to develop a machine-readable binary for each of the parameter. For that, we are using unified semantic standardized in data definitions. I will tell more about it. As you see in the picture, we have the field device in the middle. We have to serve a number of other entities from host systems to mobile devices for configuring field devices in the field, to cloud applications, as well as for analysis engines to analyze data from the field device. As Stefan mentioned, this has been started a while ago. We started, I think it was 2017, with the FieldComm Group and close collaboration with the OPC, as we decided at that time we will do a companion standard for OPC. At that time, we had already good input from the NAMUR with core parameters, and also the NAMUR open architecture use cases were an important input, which I will tell also a little bit more afterwards. There were a number of more SDOs joining this collaboration, so to support the PIDIM parameter. You see them here in the picture: ZVEI, PI, ODVA, ISA 100, VDMA, and FDT Group, which is now also owned by FieldComm Group. That was the original setup. The challenge is data is not quickly accessible or understandable. The data is distributed across many devices and facilities. Many systems, protocols, versions of tools, and people are in the data chain. Each tool, device, and protocol has a unique access and presentation of data. So you can imagine it's not easy to exchange data to get the same information if that is handled differently in all the different tools, systems, protocols. You see this little man here in the middle. It's challenging. The solution is PIDIM. It's a protocol-independent device information model. And we have a single information model across all protocols and systems. What does it mean? So yes, we have it built as an OPC UA companion specification, but we have one important point done. We have each parameter linked with a reference to a common data dictionary. So this parameter can serve as the data also for our other communication protocols. So the same parameter you find also in other communication protocols, so that this information can be distributed between different protocols within different systems. So you find this data easily in any devices and facilities. And that you need to look into, so that is quite impressive. PIDIM presents IT-friendly device data. So how we are doing that? We are using a unified semantic data mode. This is in principle coming from the NAMUR open architecture. We have an IIoT compatible data exchange using semantic IDs for machine-to-machine communication using common data dictionary. Device data can be anywhere. It could be in the cloud. It could be in the system, on-site. And last but not least, FDI is also supporting PADIM. There is mapping for each protocol available so that this data can be made available via FDI. Let me provide you some steps how PRDIM supports convergence towards IoT-enabled automation. Therefore, I provide such a roadmap in steps. So let's assume we are here today. On the left-hand side, step 1, we have a traditional field bus, brownfield. There we are using field bus protocols, PROFIBUS, whatever. We can use OPC and PRDIM on an edge device already, and we can map PRDIM from existing field buses by using FDI. The second step is to make use of OPC UA as a second channel. So especially if we have Ethernet APL devices, we could have another protocol in the devices, another channel to provide these devices for monitoring and optimization to clouds, for example. And that is one very important use case also for NOAA. So to get data into the cloud for monitoring and optimization. The third step, native OPC UA. So really to have Ethernet APL and use OPC UA for all, from the protocol for the control up to the monitoring and optimization. So you have PRDIM directly on the device level. In a simplified manner, you can look to PRDIM like the following. It's a manufacturer-independent information model. It provides you data to access the device without the knowledge of the specific device. And by doing that, you get also the semantic information. The 61987 serves here as a basis for the definition in the Common Data Dictionary. And we have a structured hierarchy within the device. So we have the device as such, which has some device parameter, and we can have special measurements, which we have in, let's call it, signals. So there we provide additional information for each device, and the device can have more than one signal. It could have many signals. And important things we are using is also to identify the device instance data by using the IL string. This is also the QR tag on the device, and that is also accessible via OPC. That's important, and also it can be used in an IDEF-ID certificate. So important is also the identification, of course, of a device to know with whom I speak. Going again a little bit more in the technical details, we standardize a basic set of device information for identification, as just mentioned with the IL string is one important part, which is normally stored here in this product instance URI. And on the right-hand side, you see here the iVendor nameplate, which is coming from the DI model for devices in OPC. So that we have been using as well, and that's very important for the first step. And secondly, then the device health. Diagnosis is also nowadays a very important topic, that everything is up and running, also with good information about what service engineer should do in case something is happening. Process variables, of course, you need for your control to need what is the measurement. That's very clear. And the key point I mentioned, exactly different here from diagnosis, is the condition monitoring. So we have special parameter also to give more information for condition monitoring, and that is one of the main drivers today also, which NAMUR Open Architecture request. But as mentioned in the beginning, core parameter, we have a number of core parameter for instrumentation special, which you can use to get a device up and running. Again, here you see you can have also a structure of devices. I will not go in all details. These boxes here are the ones which are related to one device. And in this one, you see the signal type. So there can be many signals in a device. So that is a top level architecture of PROFIBUS. I told already a lot of the NAMUR, NOAA use cases, and therefore I listed them here. They are written down in the NAMUR recommendation 176. We have use cases for health monitoring and diagnostics, monitoring of the device health, including status, possible cause, further details. We consider the device life cycle backup, storing of parameter, including history. Device dimensioning is an important use case to see if you have the right device for the right application, if you have over-dimensioned it or not, if it is, let's say, it's an optimal choice for an application. Unique identification, I said already, it's a very important point. Also, I'm coming from security, therefore it's also important. Automated as built, verify that installed devices and their configuration match with the engineered devices and configuration. By saying this, there are also some nice videos on the internet showing these use cases in more detail. Just search for them. We have general use case if we have a device with many variables, we call it multivariable devices, then you can read all of these variables and multivariable possibility check. Often users do not know what other variables are in a device, and therefore it's also important to do a check on what is available. Coming to the PROFIBUS roadmap. We have done the field devices, transmitters, valve that is released. We are looking also currently for getting more condition monitoring parameters, and special for valves. But one of the main activities in the last years were the process analyzer technology. We did it in phases. We did a phase 1 with TOC, CGA, and pH meters, and this has been released. And we also finished the phase 2 with the PGTs, gas detectors, and spectrometer. There, the release candidate is out, and this is now in the review phase. And what is now happening is, as this went so well, the people from especially also NAMUR said, we have a lot of more analyzers, and let's also get them in, because we would like to have also this condition monitoring parameters. And what we are also doing is we are looking for other things: rotating equipment, weighing, filling technology, automation technology. And the key point is, as I mentioned several times, condition monitoring. You see some information which we had in the PROFIBUS, so it's important for us to have identification where we use the vendor nameplate, we have the device health, and then we have additional condition monitoring parameters to make them accessible. So that is a target for PROFIBUS, and therefore we created also some criteria how other companion specs could become compatible, so to make it easy for a user to get this information. I draw another picture with this proposed phase 3, just to give a pre-look here. What we are planning, but it's not confirmed yet. So we have the green bullets which have been done in phase 1. We have the blue bullets here that has been done in the phase 2, and now we are talking about the phase 3. I didn't put any bullets in here because it is just under discussion. My main point, also looking to the slide before, if you wish to participate in the PADIM activities to define use cases, then please join the PADIM collaboration. I would welcome you, and that was my short update for today. Thank you very much.